right, so we're going to do some questions here for kinetics. Kinetics has to do with how fast a reaction takes place. I strongly urge you to watch the videos on kinetics that I have put in the Google Classroom. They're kind of long for this subject, but it's worth watching them to go over and review the subjects quickly. So these problems will help reinforce those concepts. Okay, so let's get going. Question 1. It gives you a reaction there. 2A plus B gives you 2C. When the concentration of substance B of the reaction is doubled, all other factors being held constant, it is found that the rate of the reaction remains unchanged. The most probable explanation for this observation is that, well, in kinetics, generally, if you increase the concentration of a reactant, you're going to increase the concentration or the speed of the reaction. So if by increasing B, it's not increasing the speed of the reaction, let's see, the order of the reaction with respect to substance B is 1. No, that's incorrect. That means as you increase the concentration, the rate increases, and as you decrease the concentration, as the reactants are used up during the reaction gets slower. And so it's not B, it's not A rather. Substance B is not involved in any of the steps in the mechanism of the reaction. Well, it must be involved in some of the steps or it wouldn't be in the reaction. So C, substance B is not involved in the rate determining step. That's probably true. It's in a step somewhere, but it's not in a step that's determining how fast or slow the reaction goes. So that looks like a pretty good answer. Substance B is probably a catalyst. Not true. If you add more of a catalyst makes a reaction go faster without becoming a part of the reaction. So it appears at the beginning of the reaction and at the end of the reaction. And if you add more of a catalyst, it's going to make the reaction go faster. The reactant with the smallest coefficient in the balanced equation generally has little effect. No, that has nothing to do with it. So the answer is C. Okay, so there's the answer for that. Okay, next question. Again, you pause these as you see fit to try and do them on your own, or just listen to me, however you want to approach this. Okay, so this is not going to fit on the screen. So the decomposition of hydrogen peroxide, we did that. That's elephant toothpaste. That's that fizzy stuff. The decomposition of hydrogen peroxide to form water and oxygen is represented by the equation above. A proposed mechanism. So the mechanism are the series of elementary steps that lead to that produce that overall reaction. Proposed mechanism for the reaction, which involves the free radicals, which is represented by the 3 reactions. Okay, so the slow step is the first step, they're saying, and then you have 2 fast steps. And the idea is if you add those 3 reactions together, you should get the reaction up at the top using Hess's law. Write the rate constant with the proposed mechanism above. Okay, so the rate law is going to be, if you reviewed the videos, and please do that before you watch this, it's going to be the rate equals the rate constant times the reactants, the concentrations of the reactants. And those concentrations of reactants will be raised to some exponent, but that exponent is not, it's not the coefficient of the reactant in the overall equation. In other words, up at the top, the original equation, 2H2O2, it is not a 2. That is not the exponent. However, the coefficients in elementary reactions are the exponents. So you've got to remember that principle. That's a critical principle to remember. You cannot use the 2 in the original reaction as an exponent. That's not it. But you can use the coefficients in the elementary reactions that make up the overall reaction as exponents. So the other thing to remember is that the overall rate of the reaction is equal to the rate of the slowest step. So if you can write the rate law for the slowest step here, you can write the rate law for the overall reaction. So we have in the slow step only one reactant, H2O2. I'm looking at the first of the 3 elementary reactions below. And since it has a coefficient of 1, then the rate law is going to be rate equals K, rate constant, times a concentration of H2O2 raised to the first power. All right, so that would be the answer to that. Rate equals K, concentration H2O2 raised to the first power. Next, The rate of decomposition of the decomposition reaction was studied in an experiment, and the resulting data were plotted. Okay, so you can kind of take a look at that. So using the graph, determine the time in hours needed for the concentration of H2O2 to change from 1.5 molar to 0.75 molar. So what I would do is just learn how to read this graph. Each of the hours is broken into 10 parts. And so if you look at 1.5 molar on the vertical axis, it lines up with a time of 0.2 hours. Be sure you understand that. It goes as 0.0, 0.1, 0.2, up to 0.5, and then 1, and then 1.5, so on. So it's 0.2 where 1.5 is. And then to get to 75, if you look over there, if you look up rather, in between 0.5 and 1.0 on the vertical axis, the up and down axis, it's halfway between 0.5 and 1. If you move over and you look at where that curve is, and you line it up down below, it looks like it's going to be 0.75 hours. Or 0.7, let's see. Again, I can't show you, I can't point it out. You're going to have to just visualize this yourself. So it's 0.75. I'm moving over to the curve, and I'm moving down, and it looks like it's 0.7. That's what I get. I get 0.75 concentration at 0.7 hours. So 0.7 minus 0.2 is 0.5 hours. So the answer is going to be 0.5 hours or 1/2 hour or 30 minutes, however you want to state that. Okay, and then it asks for 0.8 to 0.4. Again, you got to be able to read the graph, locate 0.8, and that looks like that corresponds with a time of about 0.65. And 0.4 looks like it corresponds with a time of about 1.15. So 1.15, 0.65, that's also going to be 0.5 hours or 1/2 hour or 30 minutes. You may get a slightly different answer than I did because the curve is in between grids, but you know, if you get about the same, you're good. Okay, C is a it's electrochemistry question. We didn't cover electrochemistry. I'm going to skip that. I'm going to skip D, E. Those deal with things we didn't cover. There's not a lot we didn't cover, but those are a couple of things we didn't. Okay. The decomposition of H2O2 is slowed at 298 K, but a suitable catalyst greatly increases the rate of decomposition of the reaction. Okay, so that's a fact. A catalyst will do that. Draw a circle around each of the quantities below that has different value for a catalyzed reaction than for an uncatalyzed. Okay, K equilibrium is the equilibrium constant. It's not the rate constant. Equilibrium constant is something we deal with in equilibrium. It's how far the reaction travels from left to right. How much of the reactants are converted into products. The bigger the value of K, the more the reactants are converted into products. The small value of K means very, very few of the reactants are converted into products. In other words, the reaction hardly even takes place. Here's the thing about kinetics, about the speed of a reaction. It has nothing to do with the equilibrium. It doesn't change how far that reaction will go from reactants to products. It simply determines how fast it will do it. So that doesn't change. Delta G, okay, we didn't get to that, forget it. Delta H, that's the enthalpy of the reaction. It's how much heat is going to go out of or come into the reaction. That has nothing to do with the speed of the reaction. It just has to do with how fast the heat goes out. Let's say it's an exothermic reaction. If it happens really quickly, the heat goes out quickly. If it happens slowly, the heat goes out slowly, but it's the same amount of heat. EA, so know what EA is. It's activation energy. That's how much energy it takes to get the reaction to get started and to take place. And that is something that a catalyst affects. It lowers the activation energy. A catalyst lowers the activation energy of a reaction. It means the reaction proceeds faster. So the EA will be lowered, and that's the answer to that question. Okay, the rate law for the reaction represented by the equation above is rate equals K, NO, concentration of NO2 raised to the first power, F2 raised to the first power. So again, the 2 coefficient in front of the NO2 in that reaction is not the exponent on the NO2. Okay, you got to remember that. You have to determine those exponents experimentally. Which of the following could be the first elementary step of a two-step mechanism for the reaction if the first step is the slow step and the second is fast? Okay, for an elementary reaction, the coefficients are the exponents. Again, it's about the 5th time I've said it in the last 10 minutes. If for an elementary reaction, the coefficients are the exponents. So that means if you look at that rate law there that they gave you, that means the coefficient, the rate determining, the slow step is going to be the rate determining step. So it's going to have the same rate law as the overall reaction. It's the one that determines how fast the reaction goes. So the rate law of the slow step will be the same as the rate law of the overall reaction. The overall reaction will move only as fast as the slowest step. So if that rate law is the rate law of the rate determining step, the slow step, and it has exponents of 1, then those would be the exponents on the rate determining step, the elementary rate determining step. So that means you're looking for an NO2 with a coefficient of 1 and an F2 with a coefficient of 1. And if we look at the possible answers down there, only B has that. So the rate determining step would be the elementary reaction that has a rate law that's the same as the rate law for the overall reaction, and the rate law for B would be rate equals K NO2 raised to the first, F2 raised to the first, the same as what they gave you for the overall reaction. So the answer to that one is B. Okay, keep going. All right. A sample of N2O2 is placed in an evacuated container and the reaction represented occurred. The value of the pressure of N2O5, the partial pressure of N2O5 gas, was measured during the reaction and recorded below. All right, so it says which of the following correctly describes the reaction? Okay, so one thing, if you watch the videos, if you haven't watched them, go back and watch them, is that for a first order reaction, which is the most common type of reaction, that it goes down steadily as a straight line. If you plot the time against the log of the concentration or the pressure, it doesn't matter. You can treat concentration and pressure the same. It will be a straight line. So as you go from 0 to 100, let's look at that. And it's a negative straight line. It's a negatively sloped straight line. So let's look at the first column and the third column. If you go from 0 to 100, you go from 5 to 4.3. That's a difference of 0.7. If you go from 100 to 200, you go from 4.3 to 3.6. That's a difference of 0.7. If you go from 200 to 300, you go from 3.6 to 2.9. That's a difference of 0.7. That means you're ending up with a straight line by plotting the time against the natural log, and it's a negative slope. That's why the numbers of the natural log are decreasing. So it's a negatively sloped straight line. When you have time plotted against natural log of either pressure or concentration, and it forms a negatively sloped straight line, that means it's a first order reaction. Go back and watch the videos if you didn't know that. Okay, so the decomposition is 0 order, the decomposition B. So the answer is B down there, it's first order. Okay, so now we're on to question number 5, and it gives you a reaction, an overall reaction up at the top. Then it gives you the mechanism, the two elementary reactions that will form that overall reaction. It says, which of the following is true? Step 1 represents a unimolecular reaction. Well, that kind of seems right, but I don't know if that's the answer. I'm not sure. So I'm going to move on. Increasing the concentration of NO will decrease the overall rate. That's not true. Almost never true in kinetics. Almost never. That you increase the concentration of one of the reactants and the reaction gets slower. Raising the temperature will have no effect on the numerical value of the rate constant. That's not true. The only thing the rate constant K depends on is the temperature. Think of the glow sticks that we did earlier in the year. The thing that made those glow sticks get brighter or dimmer, meaning the reaction got faster or slower, was the temperature, that putting it in the hot water or the cold water. You didn't change the reactants or the amount of the reactants at all. You just made it hotter, and that's the rate constant. So rate constant only depends on temperature. D, the rate law that is consistent with the mechanism is the rate, and they give you K NO2 squared O2. Okay, this is a tough one. I would recommend you watch the second kinetics video, the last 5 minutes, to explain this concept. I'm going to explain it to you quickly here. Okay, so the rate determining step is the slow step, and the slow step here is step 2. So the way you would write that is, I'm going to switch over to my camera. You see that it's N2O2 for the reactants, N2O2 plus O2 are the reactants in step 2. So the way you would write that rate law is K equals N2O2 to the first power, O2 to the first power. Now that's the temporary rate law. Why is that a temporary rate law? Well, let's look back at this. The overall equation, the one you see up at the very top, doesn't have N2O2 in the reactants. So N2O2 can't be a part of the overall rate law. Remember, the rate law of the slow step should be the same as the overall rate law, but it can't be in this case because the overall rate law cannot have N2O2 in it, since the overall reaction at the top, the one right under question 5, doesn't have N2O2. So what we have to do is find a way to get rid of this N2O2 and express it in terms of the reactants that are in the original reaction, which are NO and O2. Those are the only two reactants in the original overall reaction, so we have to do that. So again, watch the last 5 minutes of the Kinetics 2 video, the second Kinetics video. It explains this concept, but I'll explain it again. So here we go. So if you look at the first reaction, the step 1 reaction, it's reversible. That means it can really be divided into 2 reactions. A forward reaction where 2NO goes to N2O2, and a reverse reaction where N2O2 goes backwards to 2NO. So you have 2 reactions, and each one has its own its own rate constant, its own value of K. So when we look down here, here's the forward reaction, the 2NO going to N2O2, and here's the reverse reaction, the exact opposite. So you would write the rate law for this one as rate equals K forward, I should put an F there, times NO squared, because since it's an elementary reaction, you can use that as an exponent. You do use that as an exponent. And the reverse reaction is K N2O2, and we'll call this the reverse reaction. Okay, so you have 2 reactions there, a forward and a reverse. When they're in equilibrium, that means the rate going forward and the rate going backward have to be the same. That means that these 2 rates are the same. This rate and this rate have to be the same. It has to be going forward and backward at the same rate. That means these 2 things are the same. So we're going to go ahead and write them like that. So K forward, NO squared, and K reverse, N2O2. Now what we're going to do is we're going to solve for N2O2 simply by dividing both sides by KR. So if you come over here, I move the N2O2 over to the left side, but what I did is divide both sides by KR. So now you have KF over KR equals NO2. So now you can substitute this in the temporary rate law. So the temporary rate law is this. It's the one I wrote up at the top. And now you can substitute all of this in for this. And when you do, you end up with KF over KR times K. Well, that's a whole bunch of Ks. And they just multiply and divide together to become just one big K. And then all of this goes to this. So basically just substitute all this for this, NO2. So this just becomes one big K. And the NO squared comes down here. And then you still have the O2. So this ends up being your actual rate law for the elementary step. And that is, in fact, the rate law for the overall reaction. Since it's the rate law for the slow step, it's the rate law for the overall reaction. So let me say what we did again. The rate law for the slow step, which is our rate determining step, and it's the rate law that should be the same as the rate law for the overall reaction. But in this case, the rate law for the slow step had an intermediate in it. That's something that's created in the middle of the reaction and used up in the middle of the reaction. So it does not show up in the overall reaction. You cannot have an intermediate in your overall rate law. Why? Because N2O2, if we look back here, look at the equation at the top, N2O2 doesn't appear in the original equation. So you can't have it in your rate law. So what we have to do is find a way to solve for N2O2 using that first reversible reaction. We just break it into two reactions, which is what a reversible reaction is, a forward reaction and a backward reaction. And we write the rate law for each of those reactions, the forward and the reverse. And then we solve, we set up an algebra equation since the rate has to be the same for forward and reverse. Otherwise, it's not at equilibrium. It's still moving in one direction or the other. Since the rate has to be the same, you can set these two terms equal to each other. So there we did that. Okay? And then when we solve for N2O2, that means we divide both sides by KR. So you put a KR on the bottom here, KF over KR NO squared. And so that's what you have right there. That's just an algebra step. And so now we can substitute. We now know what this equals in terms of this. So we can substitute down there. That's our temporary rate law that we wrote up at the top. And so that becomes, down here, it becomes, let me write it out. It becomes K. It becomes KF. It becomes K times KF, I'll write it small, over KR. Okay, because this KF, KR comes down here. But when you multiply K times KF over KR, K is the rate constant in the original, it just becomes one big K. So we don't even write all that. And then you have the NO squared here, and you have the O2, which was in the original, which is in the original right there, okay? So all you've done is made a substitution. So that is going to be a rate law for the slow step, and therefore that's going to be the rate law for the overall reaction. So going back to the question, and there it is. So the answer is D. Honestly, can't tell you why A is not correct. It is made up, the reaction is made up of just one molecule. But step one is, but I don't know, that's not the right answer. Okay, next. Okay, here we go. So again, we've got a table of values. They want you to determine what kind of reaction this is. This is the one we already did. I don't know, it showed up a second time for some reason. So the answer would be first order, because for each time interval of 100 minutes, the natural log goes down by the same amount, 0.7, 0.7, 0.7. That means it's a negatively sloped straight line. Okay, let's keep moving. Okay, is this the same problem? Looks very much like it. Okay, a possible mechanism for the overall reaction represented above is, looks like the same problem, except this is not decomposition. So anyway, you're going to have to do the same thing. The slow step, no, you're not. I take it back, you're not. Here's why. Look at the slow step. The rate mechanism for the slow step is going to be NO rate equals K NO concentration times NO concentration. In other words, it's the reactants in the slow step. And neither of those are intermediates. Yeah, when the slow step is first, then it's not an issue. So it's going to simply be A. You don't have any complications when the slow step is the first step. And if you want an explanation for why that is, go back and watch the last 10 minutes or so, last 7 minutes, 7 to 10 minutes of the second Kinetics video in the Google Classroom. Okay, I explain it all there about as carefully as I can. All right, so the answer is yeah, that one's a simple one. There were no complications. When the first step is a slow step, there's not going to be a complication. Okay, we're going to keep going. All right. Blah, 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 blah. Okay, so they give you an equation up there, and then let's get to the question. At a certain time during the titration, the rate of appearance of O2, so where's O2? It's over on the product side. It's way over at the end. It is 5O2. Was, and they give you 1 times 10 to the minus 3. And then what was the rate of disappearance of MnO4, and where's that? That's over on the reactant side, and that has a coefficient of 2. So you may remember we did something like this at the very beginning of Kinetics. So Okay, so I wrote this equation. Let me draw a line here, down below the line. I wrote the equation here. I excluded all the states of matter, solids, liquids, aqueous. That's not important. Okay, now we wrote something called a rate expression. And what the idea was to equate the rate of disappearance of each of the products with the rate of appearance of each of the, of the reactants with the rate of appearance of each of the products. Okay, so here's how you do it. If you don't remember it, just learn it. You take the coefficient and you flip it, and if it's on a reactant side, it's a negative sign because it's disappearing. If it's on the product side, it's a plus sign because it's appearing. So it would look like this. And what that does is it sets all the rates, because all these things have to happen at the same time. It sets them equal. So if you don't totally understand the why of this, just learn the how you do it. This is how you do it. So it's going to be negative 1/5 concentration over change in time. Remember, we're talking about rate. We're talking about speed. And then negative 1/2 change in time. These are equal signs, not plus signs. Now on the product side, on the product side, you still put an equal sign here, but it becomes positive. Okay, and that's how you would equate all of those. So what did they give us? They told us that this appears at this rate right here, and they want to know how much did the rate of disappearance of MnO4. Okay, so we're only interested in this one and this one right here. So we're going to set those equal. So it's negative 1/2 again, this is the rate, this whole thing. It's the concentration per unit time. And that's going to equal 1/5. But we know what the rate of O2 is, the concentration. It's up here. It's this number. So it's... And so that means the rate of disappearance of this is going to equal, multiply both sides by -2, so this goes away. So this becomes over on the right side, becomes -2/5. The 2 goes up over there. And 10 to the -3. And that becomes -0.4. 2/5 is 0.4 in decimal form. 10 to the -3, you adjust the decimal and you get -4 times 10 to the -4. But a rate always has to be a positive number. We got into the explanation, so you really eliminate the negative sign. Just remember the rate has to be positive. I explained that in class, but I don't want to go into that explanation now. The negative here is offsetting the fact that there's a built-in negative here that you don't see. Okay, so it's really 4 times 10 to the -4th, and that's the answer to that. Okay, there it is down at the bottom. Okay, the equation... Okay, the equation above represents an elementary step in chemical reaction. Which of the following is the correct expression of the rate law? Okay, it's a simple one. So you do use the coefficient. Since it's an elementary step, you do use the coefficient. You only use reactants in a rate law. It's only the reactants that determine how fast the reaction goes. So that would be K NOBR squared. So the answer to that would be C. Okay, and it is. I don't know why that sign keeps coming up. All right, let's keep going. Try to get in, I don't know, about 15 of these. Okay, Kinetics experiment is set up to collect gas that is generated when a sample of chalk consists of blah, 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 blah. Which one does get to the question? It says, which is most likely to increase the rate of gas production? Last 7 words. Okay, decreasing the volume. No, that has nothing to do with the rate, how fast something happens. Decreasing the concentration. No, decreasing will make the rate get slower. Decreasing concentration of reactants makes it get slower. Decreasing the temperature. No, that makes it get slower. You want to increase the temperature if you want the rate to go faster because you want more kinetic energy in the molecules. Decrease the particle size. Yes. Just think about it. Which dissolves faster, a big chunk of salt or a bunch of little tiny salt granules? The little tiny salt granules dissolve faster because there's more surface area for the water to pull them away. And in this case, it's the same thing. The reaction will happen faster if you increase the surface area by breaking it into littler pieces. So that should be the answer there is D. Yeah, it is. Okay, next. All right. A few more. Kinetics experiment is set up to collect a gas that is generated, blah, 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 blah. Which of the following experimental conditions is most likely to increase the rate of gas production? Decreasing the volume. No. Decreasing the... That's the same question. Never mind. Sorry. I don't know how the duplicates come up, but they do. Okay. The reaction between all this stuff, again, get to the question as quickly as you can. So the question is down below that table. It says approximately how long did it take for 75% of the initial amount of such and such to react? So this is a half-life problem. Half-life is the amount of time it takes for half of the reactant to react, to become a product, or to break down, or whatever it's going to do. So think about what 75% reacted means. It means you took a half-life, so you went from 100% down to 50%. Now you take another half-life, you go from 50% down to 25%. And at that point, that means you have 25% remaining. That means you've used 75%. So saying 75% has reacted is the same as saying 25% is remaining. So that's 2 half-lives. So let's look at the absorbance line down there. And it says you went from 0.62 to 0.31. That's half of the material in 150 seconds. So that's 1 half-life. So that means the half-life of this material is 150 seconds. Therefore, if you want to go from 50% down to 25%, which is what we want, you need a second half-life. That's another interval of 150 seconds. So 150, 150 equals 300, and that would be the answer. Okay, which of the following is most likely to increase the rate of reaction? So these are just some real good concept questions. Decreasing temperature, no, never increases the rate of the reaction. Almost never. I can't say absolutely. Adding a heterogeneous catalyst. You don't need to know what a heterogeneous catalyst is. It means it has a different state, so it would be a solid versus a liquid. So that could be a catalyst does increase the rate of reactions. What about the next two? Increasing the volume? No, that doesn't increase the rate of reaction. Removing some H2. No, you're reducing some of the reactant, the H2. That's not going to increase the rate of the reaction. That's going to decrease it. So the answer would be B. Adding a heterogeneous catalyst would be the answer there. Okay, and this is the same question. Okay, C2H4 is reduced by H2 in the presence of solid platinum, so platinum's the catalyst. That would be an example of heterogeneous catalyst. Platinum is a metal, and all of those reactants and products there are gases. That's heterogeneous catalyst would be platinum. As represented by the equation above. Factors that could affect the rate of reaction include which of the following? Changes in the partial pressure of H2. That would basically you'd be adding or subtracting reactant, so that would. Changes in the particle size of the platinum catalyst. I would think so, but I'm not sure. I don't know the answer to this one. It changes in the temperature of the reaction system. Yes, that definitely would. But all three are not a possible answer. And definitely 3 is one of the answers. So it's either 1 and 3 or 2 and 3. And I'm going to say it's 1 and 3. Oh, there is a fourth answer. Oh, it is 1, 2, and 3. And that's what I thought it was. I thought all three mattered. I didn't see the fifth answer down there. Okay, it is E. So it is all three. Yeah, that should. Particle size, smaller particle size, higher pressure, higher temperature will increase the speed of the reaction. Or by changing any of those things. Okay. All right, so you got, again, a reaction mechanism. Those are the two elementary steps that make up an overall reaction. Let's see if they give you. They don't give you the overall reaction here. It says, which of the following represents the overall chemical reaction? So that's what they're asking for the reaction and the rate law for elementary step 2. Which of the following represents the overall chemical equation for the reaction and the rate law for elementary step 2? Well, the rate law for elementary step 2 is not the rate law for the overall reaction, but they're not asking for that. So let's just answer that second part. The rate law for 2 is going to be a rate equals K, HI concentration, ICL concentration. So that's going to be the only one that has that, unless there's a fifth answer again. The only one that has that is D. So you don't even need to look at the other part of the question. So that's going to be D. Okay? And it is. What if you did need to look at it? Which represents the overall chemical reaction? So you would simply add them. So you'd have H2 on the left. You would have 2 ICL on the left side of the arrow. The HIs would cancel out because one's on the right and one's on the left. You'd have 2 HCLs on the right, and you'd have I2 on the right. So that looks like, yeah, that would be D. It has to be D.